Right, let's jump straight into this explainer. Welcome to the Exam Hacker Masterclass. We're taking a highly strategic approach to cracking the Grade 12 chemistry model exam. Look, if you're a student gearing up for your finals, or honestly, just someone who's super curious about the building blocks of our universe, you are in the exact right place. We are going to completely demystify this test today. We're taking what looks like a massive, terrifying wall of questions and turning it into a really clear, manageable path.
Okay, so you're staring at the Shagar City Grade 12 Chemistry Second Round Model Examination. And yeah, at first glance, an 80-question test booklet that covers literally an entire year of chemistry, it's intimidating, for sure. But I want you to just take a deep breath. We're going to crack the code of this exam today. And we're not going to do it by just brute force memorizing 80 random answers. No way. We're going to do it by extracting the actual core concepts the examiners are trying to test you on.
So here's our game plan. We're breaking this exam down into 5 fundamental pillars: atomic theory and structure, chemical bonding fundamentals, stoichiometry and solutions, the rules of electrochemistry, and finally, mastering organic chemistry. Once you see how it all fits together, it just clicks. Let's do it.
Pillar 1. Atomic theory and structure. We're zooming all the way into the microscopic building blocks of matter.
You know, the first few questions on this exam are basically a history test on the atomic model. You absolutely have to know your history here. Take 1803. Dalton proposed that atoms of the exact same element have the exact same mass. But actually scratch that. The exam asks how this was modified. Well, the discovery of isotopes proved Dalton was slightly off, right? Atoms of the same element can kinda have different masses depending on their neutrons. Then we jump to question 1, which directly tests you on 1911, Rutherford's famous gold foil experiment. Rutherford is the guy who proved an atom isn't just some mushy sphere, but actually has this tiny, incredibly dense, positively charged nucleus right at the center.
Now this next part is pretty cool. We can take this super abstract concept from question 8 and turn it into a totally simple coordinate system. The question asks for the quantum numbers of the valence electron in lithium. Instead of panicking, just think of quantum numbers as the exact literal address of an electron. The principal number n, that's the neighborhood, energy level 2. The angular momentum number L is the street, the s orbital, which is 0. The magnetic number ml is the house number, also 0. And ms, that's the spin, pointing up at positive 1/2. So 200 plus 1/2. Boom. You just successfully delivered mail to an electron.
All right, moving on to Pillar 2, chemical bonding fundamentals. How do these individual isolated atoms actually connect to build the stuff around us? Questions 10 and 11 challenge you to tell different bond types apart. And honestly, it's all about how the electrons are behaving. If an electron gets completely handed over, that's an ionic bond. If electrons are being shared but unequally, because let's face it, one atom is being a bit of an electron hog, that's a polar covalent bond. But question 11 specifically points out that a perfectly equal distribution of shared electrons gives you a non-polar covalent bond. It's basically a perfect atomic tug-of-war where nobody wins. And that atomic tug-of-war brilliantly explains what happens when atoms combine into bigger molecules. Question 17 asks why bond angles shrink when you go from methane to ammonia to hydrogen sulfide. The secret is the VSEPR model, valence shell electron pair repulsion. It sounds fancy, but it just means electrons absolutely hate being near each other. And lone pairs? Those are invisible pairs of electrons not even in a bond, and they are extra bulky. So as you add more lone pairs to a central atom, they literally physically shove the bonded atoms closer together, shrinking that bond angle. It's a gorgeous, physical way to explain invisible molecular shapes.
Which brings us to Pillar 3, stoichiometry and solutions. Yes, this is the section where people start sweating because of the math. But we're going to translate this into clear, visual logic.
Seriously, before you calculate a single thing, check your reference sheet. The exam literally hands you anchors, like the universal gas constant, R, which is 0.081 liter ATMs per Kelvin mole. These physical constants are your best friends. They're reliable anchors you can always lean on for ideal gas questions, like finding the volume of carbon monoxide in question 47. You already have the tools in your toolbox, you just gotta plug them in.
Okay, let's tackle question 19, the dreaded limiting reactant problem. The exam gives you an unbalanced equation and says, hey, 10 grams of sulfuric acid reacts with 10 grams of sodium hydroxide. Which one runs out first? Just use this simple 3-step logic. Step 1, balance the equation. You're going to need 2 moles of sodium hydroxide for every single mole of sulfuric acid. Step 2, convert those 10-gram chunks into moles using their molar mass. Step 3, look at the ratio. Since sulfuric acid is way heavier, 10 grams of it actually equals a super small number of moles. It's totally going to run out first. So, sulfuric acid is your limiting reactant. See? No panic. Just a really logical process.
And guess what? That exact same step-by-step logic works for finding molecular formulas, like in question 20. You get a compound with a molar mass of 26 made of 92.3% carbon and 7.7% hydrogen. Step 1, just pretend you have exactly 100 grams of the stuff. That means you have 92.3 grams of carbon and 7.7 grams of hydrogen. Easy. Convert those to moles by dividing by their atomic masses, 12 and 1. You end up with a 1-to-1 ratio, so your empirical formula is CH. Step 2, the mass of CH is 13, but the exam told us the true mass is 26. So step 3, 26 is exactly double 13, right? Multiply the whole formula by 2, and your final answer is C2H2. Just trust the steps.
All right, let's transition smoothly into Pillar 4, the rules of electrochemistry. This is the wild area where chemical reactions actually generate electrical power.
The exam tests this concept heavily, especially with cells mixing copper, iron, and zinc. The one core question you always need to ask yourself is, how do electrons flow in a galvanic cell, and which metal ultimately gets oxidized?
Listen, this right here is your absolute cheat code for answering like half a dozen questions on this test. Memorize it. At the anode, oxidation happens. That's the loss of electrons. At the cathode, reduction happens. That's the gain of electrons. Just remember the old trick. Anox, red cat. In the exam's examples like question 37 with zinc and iron or the earlier ones with zinc and copper, the metal with the lower standard cell potential, which is zinc, is forced to be the anode. It gives up its electrons and oxidizes. The metal with the higher potential, copper, acts as the cathode and reduces. Lock that rule in your brain and electrochemistry becomes an absolute breeze.
And finally, Pillar 5, Mastering Organic Chemistry, the vast, wonderfully complex carbon-based world.
So many students dread organic chemistry because it just looks like an impossible alphabet soup of C's and H's. But I promise you, it is not about blind memorization. It's simply about learning IUPAC naming, which is a highly logical, universal set of rules. Think of it like learning the grammar of a brand new language. Take questions 42 and 58. They throw these massive, scary-looking molecules at you, but apply those grammatical rules and they fall right apart. Always start by finding the longest continuous carbon chain. That's your root name, like hexane or heptane. Next, number that chain, but start from the end closest to any side branches or substituents. Then, just list those branches alphabetically. Bromo before ethyl, ethyl before methyl. Oh, and if you have two methyl groups, just slap a di on it, making it dimethyl. By patiently applying these exact rules to question 42, you're going to logically arrive at the correct, long-winded name without having to guess at all.
Now, beyond naming, you kind of have to be a detective for functional groups. Look at question 60. It challenges you to spot the aldehyde in a lineup. You've got to know that an aldehyde has a carbon double bonded to an oxygen with a hydrogen hanging off the very end of the chain, usually written as CHO. It's totally distinct from an ester or a carboxylic acid like acetic acid. Spotting that CHO group immediately gives you the answer in seconds.
So, what does this all mean? We've cracked the exam step by step. But beyond just passing a test, I really want to leave you with a bigger thought today. From mapping the invisible address of an electron with quantum numbers, all the way to calculating exact yields for industrial ammonia synthesis, how will you apply these universal rules to decode the physical world around you? Because chemistry isn't just stuff on paper, right? It's literally the operating system of the universe. Keep that curiosity alive, keep looking for the structure hidden in the chaos, and you are absolutely going to crush your finals. Thanks so much for learning with me today.